For tonight's topic, we're going to talk about conditional versus absolute convergence. And this is certainly a topic that has kind of gained momentum recently on past year's AP exams, and it seems to be a more popular topic as we go. So certainly we have determined, we spent the past 3 weeks trying to figure out whether a series converges or diverges, and last night we talked about specifically whether an alternating series converges or diverges. Now the next question with regards to an alternating series is, if it converges, do we classify it as converging conditionally, or does it converge absolutely? And that'll be our theme tonight. First things first, let's do a real quick review of the alternating series test from last night. And there are 3 conditions we said had to be met. First of all, the terms actually have to alternate signs, and that's kind of the no-duh condition. But basically, you're going to spot that right away by seeing like -1 to the n, or sometimes you'll see -1 raised to the n plus 1. Something like that's going to cause it to alternate. Condition number 2, we'd say the terms have to get smaller in absolute value. In other words, the n plus first term has to be less than the magnitude of the nth term. And so anytime we put absolute values around those terms, we're describing their magnitude and disregarding their negative sign if they even had one. And last but not least, the terms must approach 0. So we'd say that the limit as n approaches infinity of a sub n has to be 0. Now at first I struggled with this, and I said it seems like these 2 conditions are saying the same thing, and I was trying to think of an exception. And the exception is, you could actually satisfy condition 2 without satisfying condition 3. Think of a function that decreases, but has a horizontal asymptote at maybe y equals 2 instead of y equals 0. And you'd have a situation where each term got smaller, but they weren't approaching 0. And so that's what's got to happen there. Now, I want to go over this number line idea really quick, because as we talk more and more about the error involved in an alternating series, I think using this number line is going to be really powerful. And let's say maybe we'll start at 0, and we're going to add a sub 1, and let's say the first term puts us right here, and we say that's the first partial sum. Well, then what's going to happen is you're going to subtract the second term, which is going to slide us back, say, this far. Now, it doesn't take me all the way back to 0 because I've already guaranteed that a sub 2 is smaller than a sub 1. So maybe the sum of the first 2 terms, s sub 2, puts me right there. But then we're going to add a sub 3, and we are guaranteed that a sub 3 doesn't take us quite back to s sub 1. Squeeze in my a sub 3. So maybe there's s sub 3. And then we're going to subtract a sub 4, which would put me right there, s sub 4. And what you're starting to see as I add a sub, whoops, I might have went almost too far. Let's say that's s sub 5 right there, is we're starting to funnel in, and we'll say the real sum is somewhere in this area right here. And I think this is a key visualization going forward before we talk more and more about error in the coming weeks. What we've seen recently is that probably the harmonic series is the most popular series out there, and his cousin, the alternating harmonic, is a close second. And so let's investigate this alternating harmonic a little bit further to set ourselves up to talk about whether it converges conditionally or converges absolutely, which is our hot topic for tonight. So we got -1 to the n plus 1 over n. And so as we expand this series, the first term ends up being a 1, and the second term is a -1/2, and then a +1/3, and a -1/4, and a +1/5, and then we continue to add or subtract based on that. And what we proved last night was that this series does indeed converge, even though the regular harmonic diverged. Okay, so tonight's question is, does it converge absolutely, or does it converge conditionally? Okay, well, actually, we're going to prove that this one converges conditionally, and the reason is that this particular series converges based on the condition that you add the terms in the order that we have them written on the screen here now. If you were to manipulate and change the order of these terms, you could actually create any sum that you want. So the fact that we're saying it converges based on the order that we have them written right here means that the series converges conditionally. Okay, so we're going to get into that a little bit more, and we'll give you some theorems to try to make this really clear cut. So as we get ready to put in our definitions for absolute and conditional convergence, let me first clarify that this idea really, I guess to summarize, it really only has relevance to us if the series is an alternating series to begin with. Typically, it's not something we're going to worry about otherwise. And so for our discussion here, for our notation here in the book, let's say that when I say the series of a sub n, let's assume that this represents an alternating series, in that there would be some kind of built-in -1 to the nth power. So let's start off with our first definition. We'd say that the series a sub n is absolutely convergent if the series of the absolute value of a sub n converges as well. Okay, and we'll look at an example to illustrate that. Now the opposite of that, we'd say the series a sub n is only conditionally convergent if the alternating series converges, but when you take the absolute value of each term, it now diverges. Okay, hence the alternating series fits into that category, and we'll try to sort that out. So as we've said, the alternating harmonic is conditionally convergent because it only converges based on the condition that we add the terms in the correct order. And so what we would say is it might look like this on a free response question. We'd say, okay, let's take a look. We've got the alternating harmonic here. And this series does indeed converge based on the alternating series test. Then, once you take the absolute value of this particular series, you basically end up getting the regular harmonic, and this series diverges. Okay, and you could use you claim p series, p is equal to 1, and anything less than or equal to 1 diverges. And so therefore, we could come back and say that the alternating harmonic does indeed converge, but it converges conditionally. Here's our second example of the night, and we've got an alternating series. And I would say, on its own right, this particular series does indeed converge based on the alternating series test. Basically, we could say that yes, the n plus first term is always smaller than the nth term, and the terms are getting smaller. We could also talk about the limit as n approaches infinity of a sub n does indeed equal 0. Okay, but what happens if you take the absolute values of this general term? We basically, that gets rid of the -1 to the nth power, and we just get 1 over n squared. And now we could say that this series also converges because it's a p series where p is equal to 2, and that's greater than 1. And so because they were both convergent, we would now say that the original series converges absolutely. So basically, if you get two converging series, we'd say that the original one converges absolutely. Okay, last example for the night. And we've got another alternating series, and we could say that this series, in its own right, does indeed converge. And we'd say by the alternating series test, and same lingo, the n plus first term is always smaller than the nth term, and the limit as n approaches infinity of a sub n does equal 0, because we have small over large. Now, let's take the absolute value of that particular series, thus giving us 1 over the natural log of n plus 1. And this one's a little bit tougher to make a decision on. Of course, it's not geometric, and it's not a clean, well-packaged p-series or something else that we're more familiar with. So I'm going to do a direct comparison test. And what I'm going to do is I'm going to compare it to the harmonic. And what I can say here is that every term in this denominator is going to be smaller than every term in this denominator. And you know how the saying goes, if this denominator is smaller, then that fraction is indeed bigger. Now you might be wondering to yourself, how in the world would I know that all of these terms in this denominator are smaller than these terms over here without using a calculator? Well, here's where we'd like to compare the graphs, and what I'll do is I'll just graph a very basic, just the original logarithmic function. The plus 1's just going to shift it 1 to the left, doesn't really affect its rate of growth. And then if I graphed y equals n, or y equals x, it would look like this. And you'll clearly see that y equals x is much taller than the natural log of x, and that's how I was able to compare the denominators and thus the fractions. Anyway, we know that the harmonic diverges, and if the smaller one diverges, then the bigger one also diverges. Okay, so let's recap what we got. The original series converges, but once we took its absolute value, it diverged, and so then I'm going to say the original one, yes, it converges, but it converges conditionally. So we'll wrap it up like this. We'll say he converges, but he does so conditionally. It's the condition that the terms must be added in a specific order in order for it to converge. All right, we'll catch you tomorrow.